So when trying to understand the second law of thermodynamics, we need to consider what the first law is. Energy is always conserved. So the energy that goes in and the energy that comes out, they balance out and you're able to find what's left. But the second law of thermodynamics, it specifies a little bit more. Basically what it says is that energy flows from high potential to low potential, and there's no way for you to extract all of it. So for a heat engine, what this means is you will not have negative heat out. If you have negative heat out, you are violating the laws of conservation. So you're going from a high potential and a low potential into a medium potential. That breaks the rules. That does not follow the flow of energy. Work out, as a result, will always be less than the heat you put in or the energy you put in to drive your heat engine. And lastly, we can also tell from that the heat going in is greater than the heat coming out. But that leads to an interesting question. What is going on with that heat that goes out? Well, eventually it mixes with the rest of the energy in the environment, and that is what we refer to as entropy. Entropy is dead energy that we will not be able to utilize. Eventually, energy reaches a certain equilibrium in the surrounding, in the environment around our heat engine. So the result is we won't be able to use it for any purpose. The heat potential collapses because everything is just properly mixed. And that's actually one of the reasons why we can never get 100% efficiency and why there is always some heat going out. We cannot extract all of the energy from a system and turn it completely into work. The output of that would be at absolute zero. The output of that would be all the way down at temperatures of absolute zero, which goes further below the floor, essentially, of our environment, of our surrounding. So here's a couple of systems that comply with the first law of thermodynamics, in that the energy we put in minus the energy we get out is the change in energy of the system, which we set a steady state for, so change in system energy is zero. It complies with the first law of thermodynamics, but not the second. This is an example of point 2a that I wrote. The heat coming out of a heat engine has to be greater than zero. And that's an example here. And this, you could argue, is the same point, but point 2b starts to explain a little bit of it. And we'll also be able to look at it this way in terms of the energy states of each input or output, respectively. Although we have 2 joules from the hot reservoir and 1 going in from the cold reservoir, giving us 3 joules, what's going on here is that this would actually be at a lower energy state, and this would be a higher energy state. So we are violating the flow of energy, which again is from high energy states down to low energy states. And that's part of the reason why conceptually, or at least this is the way you could think of it, why we draw the heat source higher up and the work lower down, and then the waste heat even lower. We are following the flow of energy from high potential to low potential. And this right here is an example of violating law 2b, which is that the work coming out is less than the heat going in. This is 100% extraction of the energy in the system, which brings this all the way down to 0 Kelvin. It brings it down to absolute zero. You have sucked more energy out than the energy state of the surroundings of the system. But then, hang on a second, how does this work when a heat pump or a refrigerator actually does this, when it pulls energy from a lower energy state and pumps it to a higher energy state? Well, that's because we add work energy to it. We are manipulating the properties of a fluid, so we create, in the middle of the pump, in the middle of the refrigerator, whatever you want to call it, a higher energy state that will then drain itself to the hot reservoir, which is, relative to our internal state, a lower energy state.